Okay. So just imagine it is Vg. I want to draw the active power, so it is Iz. Now I want to plot a VL bar. You tell me which direction will come, whether it is up or down. So Ig bar I know. Iz, I know the current, grid current I know. Where is the direction of voltage across inductance? Up or down? In inductor, current leads voltage or voltage leads current? Current leads voltage. Or current lags voltage, can I say? Our demonstration is current lags voltage. That means voltage leads current. So this is VL bar, right? Correct, na? So what is V inverter? V inverter? V inverter is equal to Vg bar minus VL. Is it so? Correct, na? So generally VIL. Yeah, so this is V, this is IL. So VL bar. Then what about V inverter? So I want to draw V inverter. So V inverter is equal to Vg bar minus VL bar. So plus VL bar is like this, minus VL bar is like this. Then resultant. What is this one? V inverter. So now is the important point here. So if this is a V inverter and this is a theta, this is a theta, and this V inverter depends upon modulation. The magnitude of V inverter depends upon modulation index. The magnitude of V inverter depends upon modulation index. Inverter modulation index will help us to change the inverter output voltage. So now you can see here, I changed the inverter voltage and then I created a phase shift. How do you create a phase shift? If I give the PWM, like with the, I have selected Vg, this is Vg. After this, after theta, I give PWM. Okay, this is a PWM area. After theta, I am giving a PWM. I started PWM. Then I will get V inverter, and then the modulation index is also such that it is in this direction. Then what will happen if I do like this? Then Ig will be like this. Otherwise, I am drawing the reactive power. That means the point here is I explained in reverse direction. So we have to explain like that only. So we take Vg and then Ig in phase. We are assuming that Vg and Ig in phase. We are identifying the V inverter direction. Once if you give the PWM like this, then you will get the Ig like this. Okay, are you getting the point? So it is like this. First we need to decide what should be the modulation index. So here the deciding parameter is what is the modulation index, what is the theta. These are two deciding parameters. But how do you decide the M and theta is if you want to transfer the reactive power or active power. So you just imagine that I want to transfer only active power, then Ig should be in this direction. If Ig is in this direction, VL is in this direction. VL is in this direction, VL negative is in this direction. The resultant Vn bar is in this direction. So this inverter with this magnitude and this theta if you keep, then you are trying to draw the Ig in phase with the Vg. That means you are controlling the inverter voltage, okay, by controlling the phase shift of the PWM pulses with the theta and with a modulation index of M, then you are able to draw the current Ig in phase with Vg. For example, the same thing I want to operate like an inverter mode. This is like a rectifier mode. So it is like a grid to vehicle concept. The same thing I want to operate like a vehicle to grid, then it should be operating like a inverter mode. So then what we supposed to do was, let this is Vg. The current is in which direction? I have to inject the power to the grid. Opposite direction. So this is Iz. If this is Iz, where is the VL direction? This is the VL direction. If VL direction is this, VL negative is in this direction, VL negative is in this direction, VR is in this direction. Okay, V resultant. Otherwise, V inverter. V inverter is in this direction. So this is phase shift is positive. That means you create a leading phase shift of PWM to get with this modulation index. So this is decided by modulation index. Then it helps us to inject the power into the grid. Are you clear what I am saying? So in case of inverter, there are two variable parameters. You know that a simple inverter, if you apply sine PWM technique, why we are applying sine PWM technique is, if you give the sine to rectangular and then we are switching, we will get a sine waveform. If you give a trapezoidal waveform and then you are giving if you are comparing with the high frequency triangular, you get a trapezoidal waveform. Okay, that reference voltage is actually is reflecting on the actual voltage. If reference voltage is sine waveform, the fundamental voltage of the actual voltage is sine waveform. So inverter is also a sine waveform, but in this case there are two parameters. One is modulation index, other is phase shift. So if you give a leading phase shift and a required modulation index to get this magnitude, then you are trying to inject the power into the grid. So this is the leading phase shift. If you have a lagging phase shift with this modulation index, we are actually taking the power from the grid. So vehicle to grid and grid vehicle to concept is covered. And sometimes we need to inject the reactive power also. Nowadays the recent grid standard says that we need to inject the power into the grid also, reactive power into the grid also. When it demands, we need to give the reactive power also into the grid. Then what we are supposed to do? So for example, this is VZ. We need to give reactive power to the grid. Then IG should be up. If IG should be up, VL bar is like this. If VL bar is minus of minus is minus, equal minus VL bar plus VG bar is, this is V inverter bar. That means if you increase the voltage in phase with the grid, but you are increasing the voltage, the inverter voltage is in phase with the grid voltage, but you are increasing the voltage with higher modulation index. Then you can basically supply the reactive power to the grid. Similarly, you can take the power from the grid also. We can take for example, assuming that the higher, like you got higher voltage because there is no loads. Just we know that Ferranti effect, assuming that we have higher loads, higher voltages at the bus, then you can actually draw the reactive power also and decrease the voltage also. How? Simple vector diagram. So this is VG and IG like this. If IZ is like this, VL is in this direction. If VL is in this direction, VL bar is in this direction. VL bar, I mean minus VL bar plus VG bar is, so this is V inverter. Like little reduce the voltage in phase. Okay, like that. Basically, the same principle we used for grid integration of PV cells also. Either electric vehicle or so and so, whatever it may be. In the previous slide, if you see, idena? Here you can see, like we basically do that. You can see here I measure IA, IBSC. Then I measure sin omega t plus 5, sin omega t minus 1. So this is for synchronization. So this is a simple rectifier we are talking about. And here, if it is a battery, this is like a battery. Like we talk about charging and vehicle to grid and grid to vehicle concept. Here, instead of this, the load, if you have a PV panels, the same control is valid. The control aspect is valid. Synchronization is anyway it is required. How do you synchronize this? There was a PLL actually. So you know that how generally synchronous generator or synchronizer, right? Here also we do the similar operation. First we will bring the voltage to the rated value and then we see that they are leading, and the synchronization is done using PLL actually. Anyway, so that is a little complex concept to explain at this point. But the point here is, if you take instead of load, this can be a battery. This battery is nothing but here. When it is a battery is there, we can do vehicle to grid and grid to vehicle concept as I explained. Instead of same load, you can have a PV like after boost converter. Like here you can have a PV followed by a boost converter. The same concept is valid for grid integration also. Why I am telling was the grid integration also the same concept is valid. Like so the inverter modulation index and the inverter, the phase shift, the phase shift of the PWM is if we vary, then we can actually inject the reactive power also, or we can inject the active power also to the grid. Okay, same concept for grid integration. Okay, this is a typical waveforms for you to understand. For example, like here the pole voltage is shown here, and the fundamental voltage of the pole voltage is shown here, and this is the line to line voltage between A and B. Okay, so this is one just example to you to show the waveforms how they are. Okay, now we will stop in taking care of how do we do the experimentation. For example, if you want to do, somebody wants to do any hardware point of view, like what are the important parameters to consider, and then what are the different sources available. So that I will discuss and then I'll close. So coming to selection of MOSFET or IGBT, like there are some parameters we have to check. One is you need to understand actually how do we read a data sheet. How do you read a data sheet is very, very important. So even somebody is teaching power electronics also, you ask your students to look into some data sheets of different switches. For example, Semicron is there. Semicron is one manufacturer. Infineon is one manufacturer. Vishay is one manufacturer. Like that, there are multiple manufacturers out there. Infineon is one manufacturer. You can get some data sheet of any MOSFET. For example, IRF 540. IRF 540, you try to ask the students to read IRF 540. But if you see that the data sheet, these are some parameters actually which are very important. One is maximum operating voltage. Like if the switch is off, it has to withstand some voltage. So what is the maximum operating voltage? What is the maximum drain to source voltage? We call that is drain to source voltage when it is MOSFET. Otherwise, collector to emitter voltage if it is IGBT. Then maximum on-state current. Maximum on-state current. How much current it will flow? Like if it is on, what is the maximum current it will flow? They are safe, actually safe operating currents. The diode will, the MOSFET or IGBT will not damage when they are operated below that value. Okay, and they also suggest a proper heat sink also. If you put that heat sink, when we operate within that blocking voltage and on-state current, the diodes, whatever, either diodes or MOSFETs or IGBTs are safe. Otherwise, they are not safe. That's what the data sheets are very important to select. What is which type of switch I have to choose, which type of diode I have to use, which type of MOSFET I have to use. Then operating frequency. Generally, there was one parameter in case of semiconductor devices that is called QG. QG means, Q means basically the charge. We say it is a gate charge. It should be always minimum. It should be always minimum. The parameter which limits the gate current is the parasitic capacitance across gate and source. For example, if you have a MOSFET, MOSFET means you know that MOSFET has three terminals, right? What are the three terminals? Gate, source and drain. But between gate is actually a metal part, source is also a metal part because we are actually giving a contact. Then you know that between gate and source, air is there is a dielectric, then there is inherent capacitance. The dielectric between the two parallel plates forms a capacitor, right? So there is inherent capacitor. But if there is a capacitor, what happens with the capacitor is, if you give a pulse, it will not allow you to change the voltage from 0 to higher value immediately. It makes the voltage profile to move slowly to the higher value. It will not move directly like this. So if you have higher QG value, higher capacitance value, switching frequency is limited. But if you have lower QG, you can go for higher switching frequency. So for higher switching frequency, if you want to go, then you should see the data sheet which has lower QG value. For example, I seen two switches. One is IRF 540, other is IRF 460. So you select, if you want to operate at higher switching frequency, you see QG value. Okay, this QG is less, so I'll use this. Okay, lower QG, higher switching frequency. We can go for higher switching frequency. And then on-state resistance. In data sheet, RDS on. RDS means drain to source resistance when it is on. So that is one important parameter to compute the efficiency. Other is, we know that another efficiency parameter is on time and off time, because switching losses depends upon on time and off time. So they are also important to compute the efficiency. And another important parameter is thermal resistance. When like in reliability calculations, this parameter is important. For reliability calculations, thermal resistance is one of the important parameter. Previously, I have shown actually in mean time to failure case that this thermal resistance also comes into picture. Okay, something like here, I have shown for IR 530, drain to source voltage, then drain current, then static drain source on-state resistance, thermal resistance between junction and ambient, and thermal resistance between case to heat sink, then turn on time, and then QG value you see here, QG is 110 nanoseconds. Okay, these are very important parameters, whichever I highlighted now. So these are very important parameters. So somebody has to understand these parameters. You have to explain the students when we are talking about power electronic switches and MOSFETs. This is a simple gate drive circuit. We know that the power switches actually, they have, every power electronic has two circuits. One is control circuit, other is power circuit. So power circuit means we have a switch, we have a source, we have a load. Okay, we know that switches is meant to on and off the circuit, electrical circuit, right? That is power circuit. Whereas control circuit means we have to basically give a control for the switch to either to turn on or turn off. So control circuits are operated at lower voltage like 3.3. Control basically can be done by either digital means of generating the control PWM or analog means of generating the control PWM. So not always don't go for direct programming of microcontrollers and then using the DSpace or FPGA. Nothing, like some applications require very small, even a 555 timer, and then simple like an operational amplifier also. So operational amplifiers we can use, or we can use a digital like Arduino Nano or something like microcontrollers also we can use. But where we are using the application is very important. So if you are simply, if you want to control the simple temperature, then I don't think that like on and off, I want to decide on and off based on the temperature. If I want to decide on and off a circuit based on the temperature, then if you want a discrete like 1 or 0 based on the temperature set value, some set value is greater than some value I want to turn on, otherwise turn off. If you want to take such a decisions, you need not write an Arduino and then take Arduino and then write a code for that. Or you need not take FPGA. You can use a simple operational amplifier also. Okay, and that is called analog circuits. Using analog circuits, we can make a control circuit, or using digital electronics also, we can make a control circuit. So power circuits is operated higher voltage, but for controlling the switch, we need to generate a control pulse. That controller actually operated at lower voltage, like 3.3 or 5, or sometimes we can go up to maximum 15. But this power circuit is operated higher voltage, this control circuit is operated lower voltage. So you need to create an isolation. You need to create an electrical isolation, otherwise the control unit will get damaged. So in order to create the electrical isolation, there are two possible ways. One is either use the transformer, that is called pulse transformer. Technically we say it is a pulse transformer. Other means of separating the control and the controller and the power circuit is using optocoupler. This is an optocoupler. Optocoupler means it has a photodiode and it has a phototransistor. Once if small pulse is given here, for example, if small pulse is given here, like 0, 3.3, 3.3, on, off. 3.3 means the current will flow, photodiode will give light, then there is a phototransistor will on. But there is no electrical connection you see here. When the diode is on, when the LED is on, here we have a phototransistor is on. Then whatever the voltage here, it comes here. So this voltage will goes to the gate and source, it triggers, okay. So finally, what I want you to conclude here from this slide is, this is a simple gate drive circuit wherein we use an optocoupler which isolates both the power circuit and the control circuit. But at the same time, we should give the pulse actually. For example, I want to operate a 50 kHz, like I want to operate this switch at 50 kHz frequency. That is my my requirement, 50 kHz frequency. Okay, I mean on, off, on, off, on, off. How many times? 50 kHz. 50 kHz I want to operate. Then what I do was, so I generate either Arduino or using simple 555 timer, I can generate the PWM, simple PWM. PWM means like high, low, high, low, high, low, high, low. Like 50% I want to make 50 kHz, okay. Then what I'll do, I can generate some simple 50 kHz frequency here at a 3.3 volts or 5 volts, okay. Then if this is on, then what will happen was, this circuit will help us, whatever the voltage here you see, plus 12 volts is here, plus 12 volts is here. If this 12 volts will come to 8th pin is directly shorted to 7th pin when it is high. That means at 6th or 7th pin of this TLP250, you will get, previously it is 3.3, if it is 3.3 here, it is 12 volts here. If it is 0 here, it is 0 here. But only thing is, in between, there is no connection actually between the control circuit and the electrical circuit. So you'll get 12, 0, 12, 0, 12, 0. This 12, 0, 12, 0, 12, 0 will give to MOSFET. So when the 12 is given, then switch is on. When 0 is given, when the switch is off. Okay. But this is about MOSFET. But when it comes to IGBT, you should give different voltage levels. It is not always 12, 0. For MOSFET, 12, 0 is fine. But for IGBT, 15 and -5. For IGBT, if you see semicron stacks and all, semicron IGBTs, they operate at 15 volts and minus 15 volts. 15 volts is for turning on and minus 5 volts for turning off. Okay, some of the PCB manufacturers, what I suggest was if somebody is starting in the hardware, then you can go to that Texas Instrument design files. There was like you just simply put TA design files. You just type TA design files. Then you can see actually some like TA design files. If you want to do inverter, you just type TA design files inverter. Then some design files will be like it will be appeared. You just open and then try to understand like what is that says. Okay. And similarly, some of the like if you know like it actually starts with the understanding the power electronics followed by PCB manufacturing. So for a PCB manufacturer, these are some suppliers. You want to develop any PCB, then there are lot of sources available. One is KiCad or OrCAD or Altium. Okay, so many PCB design softwares are available. So once if you develop the PCB, then this PCB manufacturing is done by Chipcraft Technology, Argus, Incotion, PCB Power. There are some actually who does the PCB. Sometimes you don't know how to do the PCB model also, but you know the electrical drawing. If you give the electrical drawing, they also do the PCB. They give complete PCB to you, including soldering and then mounting the device also. They directly will hand over to you the complete setup. So these are some people who does the similar activity. And then sometimes if you want to somebody wants to do some closed loop operation always demands some sensors. For example, if you want to like AC is there, it is operating at 24 degrees centigrade. So we intend to operate this at 24 degrees centigrade. Then obviously the microcontroller should understand, okay, the environment is 24 degrees per centigrade. Then there should be a sensor actually. So there is a temperature sensor which understands, okay, here the room temperature is 27 degrees, you turn on the AC. The compressor will be on. So then when the compressor is on, the temperature will decrease from 27 degrees to 24 degrees. Then what it says, okay, now the temperature is 24 degrees, then compressor, like, it waits till 23. Basically, this inverters will operate like a hysteresis control. It waits till 23, then what will happen, okay, now the temperature is at 23 degrees, you turn off. Then what will happen? It like actually toggles. It will not turn on, it will turn off, and then it will turn on only when it reaches 25 degrees. So 25, 23, 25, 23, on, off, like that that is called hysteresis control. That is called hysteresis control. But nowadays, hysteresis control was replaced with VFD control. It maintains continuously to 25 degrees. Okay, it controls the speed of the compressor and maintains continuously 25 or 24. Unlike hysteresis control, on-off compressor is not there. Compressor will be on continuously, but we reduce the speed. Okay, that is called inverter compressors. Okay, anyway, I will discuss in case of some time permits later. But so for that, we need some sensors. Here, what sensors are required is one is voltage sensor when we want to do closed loop operation. For example, DC motor control. If you want to do the speed control, one is speed means like you take the tacho generators are available. Sometimes simple small DC generators also we can use for sensing the speed of the motor, as well. Sometimes if you want to do voltage regulation, voltage sensors. So most of the LEDs we operated current control. Like we do current control for LEDs. For that we need to know what is the current. So for that we need to use the current sensor. They are LEM sensors. Similarly, a low cost solution like ACS 712, and similarly this is also one voltage small circuits. If somebody wants to do, this is a AC voltage sensor, that is both AC and DC, ACS 712. So current sensor, like hardly 90 rupees and 100 rupees. This is close to 100 rupees. Okay, like that. And some of the interfacing devices. So as I told, like we can use some simple analog electronics, or we can use a digital electronics. But in a digital environment, like so many microcontrollers are available. Like one is like Jetson Nano is a more computational intense. Somebody wants to do AA also, then you can do with the Jetson Nano, or you can work in the Raspberry Pi, or sometimes Arduino. Our people are using Arduino. Arduino DUE is a best controller for power electronics. Okay, Arduino Mega, I think you know about Mega, right? Arduino Mega, but Arduino DUE is best for power electronics. Similarly, Texas Instruments are very good actually. Texas based microchip. Texas and microchip are base, both are same. Now, so like what we use in our lab is most of the TA boards we use is 37289. Okay, is one microcontroller actually. So where we can directly use the MATLAB and then we can directly generate the PWM impulses. There is a interface is possible with respect to MATLAB. Okay, you can choose the microcontroller where the interface is possible. That becomes very easy, unlike writing a big code. Of course, if you write a big code, then it is very helpful for you to change anything in future if you know it. You can adapt it to any solution, any environment or any application. But if you are aiming for a MATLAB based, you are actually limited. But the time consumption is very small. You can first what I recommend was you can directly go with the microcontrollers which has MATLAB interface. Okay. And some softwares, of course I have not mentioned here, but TINA, TINA is one open source software where it is given by Semicron. So unlike MATLAB, if somebody don't have a MATLAB access, then you can actually work in TINA, TINA software, because we can also share the students also. That is low memory software. TINA is one software, like you can ask the students to work, especially in power electronics area. Some other softwares are like multisim, then Proteus software, then Power eSIM. So many are available. Like okay, when it comes to PCB making, as I told, like DipTrace, KiCad, OrCAD, Altium, so many others are also available. So that's all. So if you have any doubts, I am happy to answer the questions. Thank you. Anyone have any doubts, or you can raise now? Anything related to your research area? Any problem statements if you are doing? Any questions you have? So I am happy to answer. Okay, actually what our students will do was when somebody is doing on power converters, they do in a 0 PCB. So you can take a simple breadboard and then just do some small gate drive circuit, and then you implement a simple small switch. First you start with a switch, a simple battery, then switch, then load. Then you try to control the load with a simple gate drive circuit. Actually what I have drawn, that's a basic gate drive circuit. You can start with the PCB, and then you can start with that breadboard. Then you can go with a 0 PCB, means like there are some holes are there. No? There are some holes on the PCB, like the universal PCB, like we can mount and then solder everything. Circuit is not actually designed in PCB, but we have to lay the circuit using soldering. We have to put the solder and then lay the circuit. That is the best means of somebody starting in power electronics area. You work in first a breadboard followed by some universal PCB, then you can design PCB, then you can explore actually. Okay. Any doubts? Okay. Element 14 is one Mauser. Okay, okay. There are two aspects here. One is sometimes you can purchase sensor and then you build your own signal conditioning circuit. So this is one simple signal conditioning circuit I have shown here. You see, this is a voltage sensor, or sorry, current sensor. Same thing for voltage sensor. Only thing is we have to replace the current sensor with the voltage sensor, but this is a signal conditioning circuit. Okay, because the sensors will use that they are called Hall effect sensors. The sensor voltage is very small. You have to amplify, and then you have to create offset also. Because microcontrollers will read from 0 to 3.3, but the sensor, if you have positive and negative, you have to offset. Okay, you have to shift the waveform to positive. Clear? If you are unable to do it, then even boards are also available. Complete boards, signal conditioning boards are available. So one is VP electronics. You can note down. VP electronics is one. VP electronics. VP electronics. Many vendors are there, but immediately I can tell like VP electronics is one. They give both sensors as well as what to say, complete signal conditioning board. Other is Adam Tech. Adamtech is one, like they give actually IGBTs also. Adamtech is one company they give. Both the signal conditioning circuits and this one. Yeah, including BNC adapter they give. So you can directly see in DSO. Okay, you can just maybe I'll give some contacts also in case if you want to do it. Then. Hmm. 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 For high, for I mean the gain, you want to talk about gain, voltage gain. So with respect to voltage gain, you know that see why we are talking about the voltage gain to be higher is you know that in case of operation of series and parallel, if you operate in parallel, for example, if you talk about simple photovoltaics, if the photovoltaics are operated in parallel, unlike series parallel connection, then you'll get a maximum power because when of course when they are subjected to partial shaded condition. But when we want to bring higher gain, so boost converter actually because of though we say that the boost converter gain is 1 by 1 minus d, practically we cannot go beyond 0.75 because whatever the energy we are storing in the inductor when it is on, that should be delivered when it is off. So practical voltage gain is limited to duty ratio 0.75. So 1 by 1 minus 0.5 is how much? 1 by 0.25, it is around 4. So practical gain is limited to 4. But some applications desire more gain. So yes, people are working with the quadrature gains we see, quadrature boost converters, people are working. But whatever I say, the requirement of DC-DC converter, even if for the high gain converter is having low voltage stress and low current stress at the input as well as output. That is the objectives. It should have low current ripples at the input side and then low current as well as voltage stress at the output side. That's the requirement. But how do we boost? How do we boost? How do you boost is, for example, like I have a voltage source like this. So boosting nature, I can concentrate, others also concentrate. The fundamental logic of any boost converter is like this. See, you have inductor, then you are forcing the inductor to, you are charging, you are applying some voltage. So what will happen was, this voltage, if you see, the voltage becomes input voltage. When we connect across this inductor is connected across this DC source, then voltage across inductance is called VDC. Okay, so current rises. Okay, the beauty of inductor is, for example, you made it to discharge. When the current is decreases, the voltage changes actually, -2 plus. Okay, then you allow it. So previously you connect like this. You are connecting like this. Then so when the voltage changes to minus plus, so what will happen? You allow the discharge like this to the load. You allow the discharge to the load like this. That means this is VDC and then VL is adding actually. So you just see the boost concept also. VDC is there, VL is there. So we are connecting VDC and VL parallel. VDC and VL parallel. Then if you are allowing the discharge to happen like this, both VD, like of course I will draw like this. Okay, if I close this switch, the voltage is applied across this. When we open the switch, what is happening? The inductor voltage actually reverses. When the inductor voltage reverses, it is basically aiding the input voltage. Basically, it is aiding the input voltage. And then we are connecting it to the capacitance. We are actually aiding and then connecting to the capacitor. Capacitor is a stiff voltage source. So the voltage across the capacitor is now is equal to VL plus VIN. VL is equal to VDC, VDC plus VDC is 2 VDC. For example, if it is 50% ratio. Are you clear? That means you should, when you want to develop any high gain converters, only thing is you see that the charging, during charging, if it is voltage is there, you see that during discharging it should aid to the DC source. The inductor, you see that the connection or the physical connection of the inductor you place such that it aids to the DC source. Similarly, capacitors are there. So you can charge the capacitor. For example, I have like this. This is a DC source. This is a capacitor. If I directly connect, what will happen? This VDC, the V capacitor is equal to VDC. But you see that for the load, you see that the charging is done parallelly, but you see that the discharging is in series, which is aiding the DC source. So if you understand the physical structure, like capacitor polarity changes, whereas the diode polarity changes, whereas capacitor polarities remain same, but you have to see the connection such that it is aiding to the load. Okay, that is how we can develop the high gain converters. So we have to use the charging and discharging potentials of both voltage, both the capacitor as well as inductance. Okay, but the major area is to see that it has less ripples at the output. Okay, voltage ripples can be minimized. It should be minimized. Okay, one aspect in minimizing the voltage ripples is connecting the capacitor across the load. But how do you minimize the current ripples is you ensure that input side and output side have inductors in series. For example, if you see simple boost converter, the inductor is in series with the source. So input currents are less. But whereas output has more ripples. But if you see a buck converter, buck converter has inductor at the output side. So when we have inductor at the output side, the ripples are very small. Are you clear? But input has higher ripples. So you see that the ripples are minimum in both the case, both input as well as output. One simple technique is you should have the inductor at the both output as well as input. Okay, simple, like we can solve if you understand the fundamentals actually. Okay, any other question? Any other questions? Yeah. Any other questions here? Okay, thank you.